Welcome to Breadboarding. In the previous video we managed to get our CGA video controller working with the BIOS, and we managed to also fix a few issues to do with the real-time clock and generally get everything ready so that we can now actually start working on our floppy disk controller. Now the I/O board that we've already got working up here has the keyboard controller and also has a serial controller already on here, and we're going to be setting up and then configuring the floppy disk controller and the floppy disk connector up here and trying to get that running. This is video 18 in the Breadboard PC 8088 version 2 series. So we'll just look at a bit of background on floppy disk drives and when they were first introduced in the PC. So the early PC floppy disk drives were known as 5¼ inch full height drives, so you can see that this is quite a high drive here. The original PC only supported 5¼ inch drives, and initially with MS-DOS 1 and PC-DOS 1 it only supported 160 kilobytes on one side, so that was single side double density. When DOS 2 came out, it was actually able to squeeze 180k on the single-sided double density drives. When the PCXT came out, this then added the double-sided double density, so this had 180k on each side, 360k in total. The 360k is probably the capacity we would associate with the early 5¼ inch floppy disk drives. Then when the IBM PCAT came out, so this was a 286 processor version, this added support for the 1.2 megabyte 5¼ inch drives. You can see that these generally were half height drives, so were a bit thinner than the original ones, and these were double-sided high density drives. Then the 3.5 inch double-sided high density disks that we perhaps are more familiar with these days originated around 1984-85, so the 720 800 kilobyte single-sided drives became available, things like the Apple Mac and the Commodore Amiga around 84-85. The IBM PS2 and Compact Desktop 386 from around 1986 introduced 3.5 inch drives with 1.44 megabyte capacity. I should say the capacity of these is not technically correct. The actual capacity of these drives is actually 1,440 kilobytes, which is not actually the same as this, but they're generally known as 1.44 meg floppies. And from around 1988 onwards, then 3.5 inch drives outsold 5¼ inch drives. So there's a link here from a Microsoft support forum, and this actually indicates the various parameters and things for the different drives, in particular things like the media descriptor and stuff like that we will need to look at when looking at the boot sectors and things like that in future videos. We can see here with the 720 1.44 meg floppies here for 3.5 inch, and in fact we need MS-DOS 330 to actually know about the 1.4 meg floppies and MS-DOS 320 for the 720 ones. And you can then see that we've got the MS-DOS 1 for 160k, MS-DOS 1.1 for the 320k, so that's the double-sided, and then MS-DOS 2 introduced the 180k and the 380k. And then finally, MS-DOS 3 introduced the 1.2 megabyte floppy disk with the PCAT. Now 5¼ inch drives are difficult to get, and I think floppy disks are probably even harder, and I have multiple 3.5 inch drives, and I've got a couple of boxes of new disks from eBay, so I'm going to be using the 1.44 megabyte ones, and we do need MS-DOS 3.30 upwards needed to support 1.44 megabyte floppy disk drives. This is a diagram out of the original IBM Diskette controller manual, technical manual, and the key thing about this is that all PC floppy disk controllers tend to be backwardly compatible with the NEC PD765. So this was the controller chip used in the very early IBM PCs, and generally all floppy disk controllers are backwardly compatible with this particular chip. This provided two ports, one for the status and one for reading and writing data. There was an additional port, the digital output register, and this handled things like selecting which of the 4 drives you wanted to control, enabling the motor, and also whether interrupt and DMA requests are enabled or not, and handling the controller reset. Now the NEC PD765, this is the definitive guide on what various commands and things which are supported. So when we actually look into some of the various commands and things in the other data sheets, more detail will actually be included in this. So quite often those data sheets would reference this particular one. This is the IBM Diskette drive adapter. This includes the diagrams and schematics that I've been referencing. So these schematics in here, I went through in some detail in the earlier series, so there'll be a link to video 30 in the version 1 Breadboard P series where I went through these diagrams in a bit more detail, so I'm just going to skip through these. Key thing here really is the floppy disk controller on the original PC was configured to use DMA or direct memory access, and to cut a long story short, we had a lot of trouble trying to get that working, and in video 40 in fact I replaced DMA access after 10 videos trying to get it all working. Replaced DMA with programmed I/O, where the CPU basically just polls the floppy disk controller and doesn't involve DMA at all. And I will do a more detailed video, everything you'd ever want to know about floppy disk controllers, but I'm going to try and keep this one a little bit shorter, so I'm going to gloss over a number of these slides. I should say that the floppy disk controller here was actually copied over 2 pages. So all PC floppy disk controllers are register compatible with this NEC 765 chip. Later Intel floppy disk controllers, like this one, were actually embedded in PC chipsets from the 486 onwards, from around 1991 onwards. So you'll probably find that any later chipsets will actually be backward compatible with this particular 765 chip. When I was looking at a suitable design, I came across a Western Digital 37C65, and this provides all the hardware that was needed for the floppy disk controller, except for address decoding and one small issue around disk change detection. So the 4 pages of schematics that were in the original IBM PC floppy disk controller are all contained in this one chip. It's available in a 40-pin DIP package that's suitable for putting in breadboards, and I was able to get mine from about £15 or £16 on eBay. They're not available new, but you still can get these fairly easily on eBay. We're going to be using a standard 34-pin floppy disk cable, so this is 2 lots of 17 pins, and I've got a strip board DIP connector that I've made, as we've done previously, and it's based on a design by Scott Baker. Now this was actually a Raspberry Pi design, and has a schematic here that we'll be looking at in detail in a minute. And it also included the software, although fortunately all the software we need for accessing the floppy disk controller is already in the BIOS. So these are the registers we need to worry about for accessing the floppy disk controller. I won't go through these in great detail. The only thing to say is that this Diskchange bit 7 is not available on the DIP version of our chip, and so we're having to add some additional hardware to handle the disk change detection. In version 1 of the Breadboard PC, I just hard-coded the BIOS to always think that the disk had changed. So this is looking at the floppy disk connectors and cables. So on the version 1, I was actually using a cable from an old Dell PC, and this actually had some keys in the socket and the plug. And so on the motherboard side, then pin 5 actually was blocked out, and on the floppy disk, then pin 3 was blocked out. So this meant you couldn't put the cable in the wrong way. And one of the things you'll notice here is that most floppy disk cables have a kind of a twist in the cable. And what this is to do is to reverse pins 10 and 16 and 12 and 14. And if we look at actually the pin diagram here, you can see that pin 10 is motor control A, pin 16 is motor control B. So device 0 is A and device 1 is B. So 0 is A, 1 is B. And drive select A and drive select B. So in fact, by reversing these pins, what we actually do is to change drive B becomes drive A. And the reason why that's important is because with most floppy disk drives, such as this one, so the Sony one that I'll be using, that in fact in the documentation, the majority of floppy disk drives you buy actually are hard-coded to be drive 1 or drive B, and you can see down here that in fact pin 10 and pin 14 are not connected, so only the drive 1, drive B is actually connected. So without that twist cable, this would look like drive B rather than drive A. So this is the diagram from Scott's design. Now the bit on the left here is talking to the Raspberry Pi. So that is going to be different for our PC, but over here the interface to the floppy disk drive is going to be almost identical. The only thing we have to do is handle our disk change logic here. We have a 16 MHz oscillator. Virtually all of the pins going to the floppy disk drive there are just fed directly from the corresponding pins on the chip over here. And then we've got the various control signals we need to wire into our PC. And in particular, we're not going to be using the DMA terminal count, DMA acknowledge, and the interrupt request in our particular case. So one of the improvements I've done over version 1 is because the documentation for the 3765 include the pins for the DIP version on the left-hand side and the PLCC version on the right-hand side. And in fact, there's no pin for the disk change and disk change enable. And so what we have to do is to handle accessing that pin and making it available on the bit 7 of the data bus when we're reading LDCR. So that's something we'll be doing in a PLD. Now, some background that I'm going to skip over, which I'll be covering in another video, which I'll reference perhaps from the top. So this actually has the background into how DMA works. So we're going to skip through that. The main thing about DMA is all this orange stuff is really complicated and difficult to get working and is largely unnecessary if we use programmed I/O, which means we use the CPU to read and write data to the floppy disk controller rather than offloading it to the DMA controller here. This is a diagram I did in the earlier series to show how complicated the DMA was, but in fact it shows that once the CPU sends a read command to the floppy disk controller, what the CPU does is actually sits in a loop waiting for interrupt 6 to occur, which means that the DMA controller and the floppy disk controller have actually finished, but all it does just sits in a tight loop there waiting. It can't do anything more useful. And then this is the simplified diagram that shows once we send the command to the floppy disk controller, the floppy disk drive reads a data byte and keeps on reading bytes. We poll the status of the floppy disk controller status register, we read the data, we write the data to RAM, we increment the address, we check to see if we're still in execution or if we're in results phase, we go back, check the status register again and continue that until such time as we hit the results phase. Then we have to read the status information and then complete. Now there are some complexities around the end of track EOP errors because we're not using DMA, we don't get the same termination signals that the floppy disk controller expects. So we don't use DMA or interrupt 6. So there's a lot of background here which I covered in the earlier series, so I'll include a link up here to the video 40 where I covered all of this stuff. There is a lot of information available in the PCJr guide. This technical document includes all of the BIOS listings. They include all the code for accessing floppy disk. It also includes logic diagrams as well, which includes the watchdog timer facility here, which I'm excluding from this particular design. On this link here, Ricardo's actually reverse engineered a lot of that BIOS source and is available on the site here. And what you can do is actually download these various files. In fact, this IBM PCJr BIOS.list I've got downloaded, and this is what I use to base a lot of the code on here. And you can see here, this is quite nicely formatted, and the disk accessing routines, disk I/O is down here. We've got the disk read, format, write down the bottom here, and then the RW operation. This is actually where the majority of the logic that we require to actually copy out of the PCJr BIOS and put into our XI8088 BIOS so that we can do programmed I/O. And these, the verify loop, the read loop, and the write loops are basically where we replace the DMA with the programmed I/O. So it's the CPU that actually goes around in this loop. And this is where I have needed to tune things a bit to enable it to work fast enough so we don't miss out any data. So we do need to disable the DMA and the interrupts, and there's also a bit in something called the specify byte, which is part of the instruction sent to the floppy disk controller, and we need to disable DMA in that bit as well. And because we no longer use interrupts, then the FDC wait IRQ routine, which is used in a lot of the existing BIOS, is replaced with this check status 2 from the PCJr. And this just shows a comparison between the PCJr, and you can see here that the original PC was able to do up to 4 drives. This can only do 1 drive. And because it doesn't have all the DMA and interrupts, then in fact it adds this timer here such that if something went wrong with a floppy disk drive, after 3 seconds it would time out, and there was some code to do to handle this. We don't need to worry about that for our purposes. If you're trying to do a PIO mode commercial drive, then you probably would need to include this watchdog timer. One of the key things I did find with the original Western Digital datasheet is that there were a number of errors in it. So in fact, a lot of the references for the tables were incorrect. So I have annotated this version. So the references of various tables are incorrect. So in fact, the master status register is listed in table 6.1, which is not in fact correct. And in fact, this says it's status register 0. In fact, this is the master status register. And in fact, the references on these other status registers are generally 1 out. So you can see here, I've corrected this in this particular document. Now, it doesn't really matter too much when you're doing the hardware, but when you're trying to get the software to work, then it's quite confusing to have this. So if you are looking at this, just be aware that this data sheet is not correct. This is just comparing the IBM Diskette drive adapter documentation with the Western Digital datasheet, and there are a few minor things to be aware of, but nothing majorly significant. The main thing is that when we're using PIO mode, then in fact these 2 bits, D7 and D6, when these are 0, this is how we know that it's been successful. And in one of these registers, the 2-sided mode is now replaced with write protected. I guess that this was 10 years after this version, really everything was double-sided from then on, so it is now used for write protect. There were some differences in the code to do with the DOR register, which the PCJr had different bit mappings from the original PC, so we needed to take that into account when doing the code changes. And this was how the PCJr would use the command 8 sense interrupt status, and this returned the status 0 register value and also the current track number. And we also needed to make sure that we set the non-DMA bit on this particular command as well. So by default, this would have always been set to 0 on normal PCs. We need to set this to 1 to disable DMA. Similar configuration in the BIOS parameter block in boot sectors, so we override this actually when we read the data off the disk. The main issue we need to be aware of about handling the interrupts is we don't have interrupts anymore, and when we actually get the last bit of data, we need to compare the number of sectors requested versus the number of sectors returned. If those match, then we know everything's okay. If they don't match, then there's been an error. And there's some more background detail here that I went into in video 40, should you want to go and look at that. So the main problem I had when doing version 1 is that the PCJr was used to work with 360K floppy disk drives. Now these worked at about 250 kilobits per second, so that's about 31 microseconds per byte. But the high density floppy disk drives actually work at twice that rate, so they use 500 kilobits per second. That only gives you about 15.6 microseconds per byte. Now the problem is the original PCJr BIOS code was not quite fast enough at the default PC frequency for that, and so what I had to do in version 1 is improve the efficiency of the code by changing some of the instructions to make them shorter and more efficient. And I also increased the clock speed in the original one from 14 MHz to 16. Now what we're doing in this one is, because we're using an Intersil processor which is capable of working up to 8 MHz, what we're actually going to do now is to use this dot clock, VGA dot clock frequency divided by 3, and that will give us about 8.3 MHz, which should mean that we won't miss any of the data. When running at the standard frequency, we'd miss about 5 bytes out of every 500, which obviously would cause a problem. And this is just a diagram showing that when we were using DMA, when we were reading the data from the floppy disk controller and we were writing it to this address here, 7C00 is where the boot sector goes. You can see that the time between subsequent reads of the data and writing to the memory here were about 15.6 microseconds. Then this is the updated PLD for the external I/O decoder, and you can see here that we've got the floppy disk controller chip select, the operation register chip select, and the configuration register chip select, and we also output the Diskchange input here from the floppy disk. Goes to bit 7 of the data bus when we have LDCR and the I/O read selected, and we can see down the bottom here that we've got the rules for the chip selects there. We also have the output enable for XD7 is only when we're got the configuration register and we're reading that register, and we just output the Diskchange bit there. So that should hopefully address our missing Diskchange bit. So we just need to go off and compile that, burn the PLD in, and then we're going to lay out the changes. So just going to program the PLDs and then start wiring up the board. Now the BIOS already has most of the changes we need. The only thing we really need to do is to make sure that we enable the Diskchange support. So I'll do that and program that, and then when we come back we should be ready to see if we can actually access a floppy disk. Just going to disconnect this from the main board so we can work on it a bit more easily. The address lines, I/O read, I/O write, various other control signals, and the data bus. Keyboard, serial port. Go off and configure that. Okay, so I'm just going to reprogram this decoder PLD. It hasn't actually changed much, but I just wanted to make sure that the PLD actually matches this, and I've already updated the chip label on it. This is the PLD, so the rules haven't actually changed. It's just that the floppy disk controller line there, I've changed the label of it. So this is just to make sure that it's consistent. I've also updated the chip labels. They have the I/O decoder version 4 and the external I/O PLD version 2. So I'll just read the current chip, make sure I've got it in right. This is the I/O decoder 2 version 4. That's programmed, just put that back in the board. And then do the same for the I/O decoder here. The only downside of having the wires a bit too close here is it makes it a bit more difficult to get the chips out. We need to leave at least one pin gap between the ends to make it easy to get out. This is the external I/O decoder. This is now version 2, in that we've now got the floppy disk controller line coming in here, which is for the 0 to 7 range, and then we're outputting the floppy disk controller chip select, which is just 2 of the ports, and then the LDOR and the LDCR as well, all coming out of there. So the FDC chip select is 0F4 and 0F5. Then we've got F2 and F7. I've already compiled that. We'll just read the chip. And this is the external I/O version 2. And we'll put that back. I'm just going to unplug some of the ribbon cables here for the data bus so you can see things a bit easier. Just move these out of the way. Okay, so we're going to go off and wire up the power. So we've got to wire up this chip over to here, and there are a number of connections also need to go from here to here. So we'll come back once that's all wired up. Okay, so we're going to wire up the floppy disk connector and the power lines and the pull-up resistors there to 5 volts. So the left-hand side of the floppy disk connector has virtually all of the pins grounded. The only signal's on the right-hand side there with the label. I'm just going to wire in the oscillator at the top there, leave room for the power connector there, and put the oscillator clock into the floppy disk controller, and then the power lines for the FDC, the pull-up resistors for the various pins that need them. Then we need to wire in the Diskchange, which is the thing which isn't handled by this dip chip, and the address line 0, which is buffered from the PLD down to the left there. That's the address line in there. Now I need to wire in the floppy disk controller chip select line from the I/O decoder there, and also wire in the data 7 line for the Diskchange. Now we're going to wire up the I/O read and I/O write, and the operations register and configuration register chip enables. The operations register is 3F2 and the configuration register is 3F7. Then we're going to do the reset and the floppy disk control line, and that is for the 3F4 and 3F5 addresses. Now we're going to start wiring in the floppy disk connector pins. So we're starting with the receive data, index, side and identity select pins. Then write protect and the W gate. Then the write data, step and direction. So step and direction controls changing the tracks of the floppy disk drive. And then the motor B and drive select A. So that controls the sort of drive 1 motor and the drive 0 enable, and then the disk select B and motor A. Then we'll just check that we've done all the pins we needed to do, other than the data lines there. I'm just going to swap out this cable, which is a 5 and a 3, but it's just quite long. I'm going to make it made up this cable, which is a bit shorter. And then this can go back to the buffer over here. Let's plug this one over here. Okay, so finish wiring that all up, so we should be ready now to plug it back into the breadboard PC. So I've just reminded myself of what the connections we need. So we've got A0 to A7, we've got the active low reset, the IO 3XX, IO 0XX, so those are like the decoders for some of the IO ranges. Nothing here. Then we've got IRQ12 for the mouse, IRQ1 for the keyboard, direction goes to DTR, then we've got D0 to D7, and then IO read and IO write need to go into these two sockets over here, and then IRQ4 is over here and comes out here, so we might just wire that straight into there, and then that should have everything wired in ready to go, and the power connector goes up here. So when we come back, I've wired it all in to the rest of the breadboard PC. We'll connect a floppy disk drive and see if we can boot up an operating system. Okay, so I've plugged the I/O board in here, and you can see we've now plugged in the floppy disk cable over to the floppy disk drive there. So I've got an MS-DOS 330 floppy disk in there. I have tested that the disk and the floppy disk drive all work in an old compact Despro PC I've got access to. So I know that that is working, and it's using one of these crossed floppy disk cables. So most relatively modern floppy disks come with drive B configured, and this twist is necessary to turn it into drive A. So that's why these cables look like they do. Now I've also reconfigured the BIOS so it now supports turbo mode. So this means that one of the registers, the port B registers, one of the bits there can be used to switch between the default 4.77 MHz mode and the turbo mode, which is in fact 25 MHz divided by 3, about 8.3 MHz. So I'm just going to turn that on first of all, and we'll have a look and see whether or not we can configure that first of all. So I'll just show the video capture here, and as we power it on, I'm going to press F1 to go into the BIOS setup. So just going to boot the BIOS, and as it comes up, we're just going to press F1 to go into the BIOS configuration. I'll just make that full screen. So what you can see here, 3 or 4 lines down, main processor, Harris designed, 80C88 at 4.77 megahertz. So now the BIOS has been extended to include the sort of turbo mode extensions, which allow it to select the CPU speed. And if I just quickly switch over to the oscilloscope, you'll see that the current frequency is about 4.7 megahertz. Here you see the oscilloscope probe is on the main CPU clock here. You can see it's about 4.77 megahertz. And what we're going to do here, we just type C for CPU, and now we're going to hit T for turbo, and then we're going to save that and reboot. We'll just reboot that. Now you'll see actually about 4 lines down, you can see that the 80C88 at turbo, so it's now actually running at the turbo frequency. And in fact, if we switch back to the oscilloscope, you can now see on the oscilloscope that in fact the frequency's increased slightly. It's now 8.39 megahertz. So it looks like the turbo mode on the BIOS is working okay, and we are going to need to run the Breadboard PC in turbo mode to be able to read the floppy disk drive fast enough when we actually come to reading data. But you can see here that it's actually failing to boot. Now each time, I'll just turn this on and we'll go full screen again. We have the boot power on sound, and you'll see here that the floppy disk drive light does come on, but it does come up with boot failure. Now I've been looking at this for a number of days now, and I have got a logic analyzer signals all over the place, but I still haven't been able to get to the bottom of why this is not working. So for the moment, what I'm going to do is going to leave it here for the moment, since we're already up to probably 35 minutes or so. And so in the next video, hopefully we'll be able to sort out any of the teething problems with the floppy disk controller, and we'll be able to boot early versions of MS-DOS. So if you don't want to miss out on future videos, please hit subscribe, and if you found the content interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.